So this is my favorite part of the evening because I get to introduce the speaker. So tonight's talk is about performance, and it's slightly controversial because anytime you bring up performance, people have opinions. Some people think this is right, some people think that is right. So I'm so excited to have John here to give us his opinions on performance and talk about why some of the things that he's working on are so great and why we should use them. So he's a lead engineer at Conversant. He's the creator of the Conversant Disruptor. So if you've ever heard of the LMAX disruptor, that is another thing that helps your code go very, very fast. And he's a mentor and high performance Java specialist. So without further ado, I'm going to stop talking and hand it over to John.
All right, thank you, Bob. So we'll adjust the volume while we're getting started here. All right, so I know why you're all here. Thank you for joining us on Cinco de Mayo. Hopefully you guys all had a couple margaritas, so you're nice and ready for this Java concurrency talk. But you know, I'm pretty sure you're here for blood, right? Superman versus Batman, right? You want to see this? You want to see the throwdown, the fight? Or for you Marvel guys, we've got Captain America versus Iron Man. No, I don't know. I'm a big fan of Tony Stark and Iron Man, but I think he's wrong about the whole registration of superheroes thing. I'm against him on the Civil War thing, but anyway, just you guys not taking a side. All right, but anyway, not to disappoint you, but this is not going to be a throwdown between the two disruptors. This is a talk about concurrency, and I'm basically going to try to cover every mechanism of Java concurrency that you can do. And you know, I'll start at a very primitive level and move up to sort of the Java level. So we'll talk about the machine models and programming languages model. But you know, I'm going to be basically, there will be a little bit of like don't hurt me, and then we'll eventually end up in the ultra violence. So you guys can hopefully there'll be something for everybody. All right, so processor performance. I can't really go too deeply into this because my talk is fairly long, but to make a long story short, of all these things, you know, clock rate, changing the microarchitecture, superscalar, right, pipelining, these are all really hard problems to solve, and scaling up your CPU performance that way is not an easy way to build an application. So what are we left with? We're left with multiprocessing, right? So just informal survey, who in the room works on an application that has, say, 10,000 or more threads? Is that something nobody's seen that? Has anybody seen any like exotic environments where they have like hundreds of thousands of threads? Right? I mean, this is just sort of the frontier, but that's where things are heading. It's, you know, it started out, you know, you can remember maybe 20 years ago, or those of us who remember 20 years ago, you know, applications had 1 or 2 threads, and it's just expanding out from there. So really, that's the problem that we're facing, is how do we deal with the multi-threading of things to improve performance? So what's concurrency? Concurrency is the property of a program or a problem that it can be decomposed into ordered, partially ordered, or unordered units. Now I put wiki-esh on here because some of it's from the wiki, but I actually added the unordered part because really, what's the goal of this whole discussion? The goal of the discussion is that we have unordered code that executes. Basically, that means it's in parallel, right? So the reason that you have concurrency, right, is to be able to get to the part that's unordered, that can run in parallel. And you know, you have Amdal's argument that says that basically the amount that's ordered or partially ordered is going to determine the performance of your application, right? So that's what this is all about. So how do we approach concurrency? And the first thing I want to point out before we dive into all the specialized techniques is just a simple one. It's just design. So I've seen a lot of cool systems that are designed to be stateless, right? You can build it, especially in the web environment, or if you're in a microservices environment, you can store a lot of your state, you know, either in a browser URL or in the browser, something like that. So you don't have to have state within your application. So if you build and design your application to be completely stateless, then you don't have a concurrency problem. You can totally eliminate that from the equation. Now you might have other problems, but that's what you'd have to work out. Failing that, right, that doesn't really work for people that deal with a lot of data. So maybe you can design your system so that it's immutable. And there's certain sort of, boutique, I'll call it, and people will be like, they're not boutique, it's what I use every day. But there's certain boutique languages, right, that, have sort of a major design principle around immutability. Let's make everything immutable, and by doing that, we completely eliminate concurrency issues from the equation. So if you can't achieve that, then we're left with what we can do in Java to achieve synchronization. So we have the synchronized keywords, the most basic form of concurrency that we can achieve. There's locks, unstructured locks in Java. I'll talk about that. I'm going to talk about something called read, copy, update, and actually the whole kind of second half of the talk will be loosely related to that concept. Obviously, I'm going to talk about atomics, and then eventually, at the end, I'm going to make you guys wait for it. I'll talk about queuing strategies. All right, so starting with synchronized keyword. So the thing I want to say, and I found this, really dark and ominous picture so that you guys can get the right impression. It's not as bad as you think, right? Like, as soon as reentrant lock was introduced, like everybody switched over to it. It was like the cool thing. So, synchronized must be bad, right? So that's why they introduced reentrant locks. But it's not as bad as you think, I would say. The hotspot JVM has it so that it can eliminate it. It's actually implemented as a built-in, right? So the JVM is free to re-implement it, right? In a future version of Java, maybe they'll, use disruptors to implement synchronized, and we won't even have to have this doc, right? So that the JVM could be optimized without you changing your code. If your code is overprotective and the JVM can detect that, then it could probably eliminate the synchronization. So that's a nice feature of synchronization. It scales well with I/O operations, so if you're protecting some I/O state, it works really well for that. And I'm sure everybody knows that you don't want to use it in a tight spinning loop. And I will kind of talk about those timescales towards the end of the talk. I'll give some specifics. Okay, so how are we going to set up the problem? How are we going to talk about the problem? Let's talk about what a data race is. So a data race is the condition resulting from unordered access to a memory location when one of those accesses is a write. And that sounds like, whoa, what did he just say, right? But if you look at the code, it's really simple. You have one thread that's reading and one thread that's writing, and they're essentially unordered. You don't know when this is going to happen. So there's racing going on here. They're both having access to P1. And so you don't know which is going to happen first, so you don't know what value of P1 that read thread is going to see, or if it even sees a valid value. I'm going to treat this where there's two shared memory locations because I know you guys are all experts and you're going to understand the simple case. So I'm going to go with a little bit more complicated case because it'll make some of our examples later more interesting. So let's break it down. So what happens? So we can assign P1, we can assign P2, and then we can read the values, right? And then it's what everybody would expect. There's another case, right? You assign P1, then some other thread comes in and tries to read P1 and P2, but oh, you can't because P2 hasn't been assigned yet, right? So it's out of order. So P2, and the result is undefined. This case could also occur, right? This is the case where you try to read before you've written anything. That can happen, obviously, when things are unordered. And I think probably this audience is astute enough to recognize this case as well, right? You can assign P1 and P2, and if P1 and P2, this is executing on a separate core, and that core has P1 and P2 in its cache, then this may still be looking at an invalidated region of memory, right? It could be cached, outdated value. So this is what we're trying to solve when we deal with any of these concurrency problems. So you guys all know the answer to this, right? You synchronize it. And if you synchronize it, it causes the accesses to both the read and the write to be ordered. And this solves all of the problems except for this one, right? So usually what people do is they contrive their program in such a way so that the write happens first, or they set up some suitable default, right, so that the read will read something useful before the first write happens. Okay. So how is synchronize implemented? Every Java object instance, running in the JVM, has a monitor object associated with it. I'm not talking about the bytecode or the class. I'm talking about the Java object, like the OOP, the thing that the OOP points at. And so basically what you do is you try to acquire that monitor. If it acquires it, it can proceed to the critical section Otherwise, it has to suspend the thread until the lock is available. Now, I want to talk about synchronized in terms of it being relatively fair. And I mean in comparison to some of the things that we're going to discuss later. So kind of keep that in the back of your mind. Generally, we don't even consider the fairness of synchronized. It's so fair that it generally works. But fairness is a really hard problem, right? Even if synchronized was completely fair, your thread might not get scheduled if it has a lower priority. And even if your thread scheduling was completely fair, your process might not get scheduled if it has a lower priority than some other processes. So fairness is a hard problem, and synchronized doesn't claim to solve it. But it's fair compared to what we're going to discuss. Just one little problem with that code I already showed you about throwing the synchronized out there. What if somebody else comes along and takes your object that you've made concurrent by making every method synchronized, and then they lock it, right? Can anybody see the problem here? Anybody want to hazard what the problem might be? Yeah.
Well, it's still the same lock they're locking on.
They're locking on the same lock. It's a shared lock, right? And this is going to be, you want to grab a t-shirt. This is going to be a denial of service on the write, right? When somebody comes later to try to write on this object, it's going to be held indefinitely by this loop here. So that's a problem. We can easily fix it. What we do is we allocate an internal locking object. And so then we synchronize on that, right? And I think all you guys are still with me, right? This is pretty basic stuff. Right? But if we're going to lock on some internal object, maybe we ought to go with reentrant lock, right? So what does reentrant lock do for us? So introduced in Java 5. Now, it's interesting because the constructor actually allows you to tweak the fairness setting. So I talked a little bit about fairness. The normal setting, which is fairness equal to false, it just behaves like the synchronized keyword. It's the same kind of fairness. If you set fairness equal to true, then Java will do its best, or the hotspot will do its best, to schedule the threads in order that they attempt to acquire the lock. Okay, and that makes sense, right? But at the expense of some performance. So if you set fairness equal to true, it's a harder job for the JVM to actually achieve, and you'll have to pay for it. It also adds interruptible waiting, which is nice, right? So like this always happens in like an old school application 20 years ago. Your application would crash on exit, right? Because you have one thing walking on the monitor, right? And so it has interruptible so that if something's exiting, you can interrupt those threads and it actually goes out. So that's kind of nice. It supports unstructured locking, but I hope you don't use it. We should all be trying to eliminate naked locks, unstructured locks. All your locks should be in a try finally block, right? I mean, it just doesn't make any sense to return a lock object and you don't know if it's locked or unlocked, right? That just leads to bugs. So it supports it, but I hope you're not using it. It's a library function, right? It's a library class. So there's fewer optimizations available to the hotspot in terms of how it executes. This is, it's obvious, right? This is a prescription. It's in the code. It's telling the hotspot how to execute this code. So it can't make the same level of granular optimization to it. It just can kind of apply the general rules that applies to everything else. Okay, and then so there's a refinement of that. Consider the problem where you have a lot of readers and only one writer. I said it wrong again. Consider the problem where you have a lot of readers and one writer. There. Finally got it out. So an example would be like a configuration thread, right? That's reading from a file like every minute or every hour. Or maybe it's reading from like a database table, right? Or consider like a cache management problem, right? What's the typical cache management case is that an object is really expensive to construct or to build or to fetch, right? But then you have a lot of things that want to read it frequently, right? So that's the kind of case so you have an asymmetry in how things are read versus how they're written. And so for that case, we have something called read-write reentrant lock, or reentrant read-write lock. And the idea there is just very simple. There's a read lock method that allows you to actually acquire the lock, and then at the same time, another thread, if this lock even is already held with a read lock, it can then acquire it again, and another thread, and another thread. So it actually allows parallelization for the reading. So that's nice, because one of the challenges, right, that we face is kind of getting things to be able to run unordered. Now, unfortunately, there's a downside to that. So in order to acquire the write lock, it could be starved by the readers. Let's say the readers are always holding on to this read lock, right? Then you could never acquire the write lock. In order to fix that problem, you have to resort to the fairness equals true mode, where it tries to schedule things in the order that they attempt to acquire, but that's expensive. It supports downgrading from the read to the write, so if you hold the write lock, you can call the read lock, it'll be successful, and then you can unlock the write lock and it'll allow you to downgrade. Now you got a read lock and not a write lock. It doesn't support upgrading. That's a hard problem. You'd have to understand the fairness of the algorithm to be able to solve it, and there's no reason why anybody would want to do that. Okay, honorable mention, just a couple things. The first time when I practiced this talk, some people said, but you didn't talk about every type of concurrency in Java. But I want to debate that. I think it's a little bit of a fine point, because there's different, what I'm going to call concurrency strategies in Java: semaphores, latches, phasers, delay queue. They're all based on the same abstract queued synchronizer implementation, or several of them are. So it's basically like the same thing as a reentrant block. And I'm not really interested in these different strategies, like whether or not you use a semaphore. I'm talking here about the fundamental way that we achieve concurrency, right? So how you would implement a semaphore, not how you would use a semaphore. Does that distinction make sense? All right, so let's take another little just detour for some definitions again. Happens before. Okay, so access to A happens before B if A occurs before B in the same thread, okay? Or if A synchronizes with B in a synchronization context. And you guys are all saying, duh, right? Like that's how we all thought it worked. But I can tell you that that is not obvious, that there's no programming language memory model before C++ 11 that said that that is how it has to work. And so as programmers, I'm sure we all assumed that that was the way that it worked. But it doesn't have to. There's things like reordering and stuff that I'll talk about in a little bit that mean that this is not necessarily the case. But in a big way, C++ 11 stepped up and they said, okay, we're going to define this and say this is what we're guaranteeing. See, if you use C++, you'll have this behavior. And it's nice for programmers, right, because it allows us to actually expect the machine to work the way we write our code. So causality, like you physics buffs will be like, of course there's causality, right? If A happens before B, then any thread that sees the effect of A will see the transitive effect of A. And again, you guys are like, of course, right? It's a law of the universe. One thing causes the other. But this is not true, actually, in a lot of machine architectures. So in machine architectures that have weak memory models, like Digital Alpha or IBM Power Architecture, or a lot of sort of more modern architectures than Intel, you don't have causality. And actually what a lot of those architectures support is something called speculative reading. So that if you're doing a write, a speculative read can jump in front of your write because the read is always faster, grab an undefined value out of the air and return that to your code. Right, so you shouldn't sit there and say, oh, I've got causality, my code, I can depend on that. But in Intel, the x86 architecture is old enough that it actually has this built in. And we'll kind of talk a little bit. I don't have time to really get into the strong memory model of Intel, but Intel's memory ordering and model is so strong compared to these other architectures that we have some of these things, and we can take it for granted at times, and we can also take advantage of it to write really high-performance code. So sequential consistency, the typically false assumption that programmers assume that the operations of a single thread interleave with the operations of another thread. Now, I think I know where this comes from because, we probably all had that experience in high school or college where we're like asking somebody, how does multiprocessing work, right? How does parallel processing work? And they probably said, well, the thread is running and then it stops and another thread starts running and then it stops and then the first thread comes back and it starts running. So the way you got it told wrong, right? That's actually not how it works. And the reason I put typically false here, that's not Leslie Lamport's wording, that's my wording, is because there's never been a machine architecture that was built that supported sequential consistency. So even though you all thought that that's how it works, it's never been done. And the reason for that is incredibly excruciatingly difficult to implement a practical system to have this characteristic? I mean, it basically means that every operation in your system would have to be single-threaded. So now we're getting to the more interesting stuff. So the programming language Ada kind of pioneered this discussion around having strong memory models or having application support for parallelization and vectorization and building sort of the memory model in. And that was actually, I mean, you know, decades ago, right? A long time ago. So this is a concept that comes from the Ada world, but there is no interleaving of operations A and B such that if A or B write the same memory, that would cause a conflict, right? I already talked about it, what a data race is. So a simple way to say it is data race freedom means that there aren't any data races, right? So A is not writing B, B is not overwriting A, they're not interleaving like that. So you guys are like, you're talking about C++, you're talking about Intel, but you're not talking about Java. So let's talk about Java. Okay, so Java is data race free. Well, so they say. But academics dispute that Java can be data race free, and here's why. There's a couple of features of Java, common sub-expression elimination, right? So you have a method, C equals A plus B. And then somewhere farther down in the same method, it also has A plus B. So what the hotspot will do is it'll take the value, you know, A plus B, calculate it, put it into C, and then later on when it encounters that same expression again, it just plugs in the value C. But right, that's obviously a data race, because what if some other thread came along in the intervening time and updated A or B, right? Then you get a different value, so that's not data race free. The other thing that the hotspot will openly do, and they say that it's free to make this optimization, is to reorder things, right? So reads and writes can be reordered. A lot of times writes are put to the beginning of methods because, you know, writes are very expensive, so they want to get them happening as soon as possible. So, you know, the instructions can be ordered in weird ways by the optimizer, and if any kind of reordering at all is going on, you probably can't be data race free, because what if somebody else changed it, right? Then you're going to be depending on when they actually changed it to make that work. Now, I already told you that we can kind of depend on the fact that Intel has a very strong memory model, but just remember, if the hotspot is free to reorder operations, that all goes out the window. So that, you know, Intel's going to say, if I get a read and then I get another read, these are going to go in sequentially, and they're guaranteed to be seen the same way on every processor. But if Java reorders those reads, then that's what the Intel processor is going to see, and that's going to determine what you get, right? By the way, I'm going to talk a lot about Intel. Is there anybody here that's not working on Intel regularly as their main thing that they're working on? Okay, so I won't spend too much time talking about exotic architectures, but kind of keep it to the Intel focus. So anyway, what's the consensus, right? We don't want to go down this road of having this huge academic debate about concurrency. What can we do? So Java defines explicit concurrency tools. So you should basically assume that your unordered code is subject to deliberately weak constraints. If you're not ordering it, then it's not ordered, right? That's what you have to take home from this whole thing. Okay, so back from the detour. Any questions up to this point? So yeah, this is all sort of stuff that most people who are familiar with concurrency have at least seen or heard of, right? Okay, read copy update. How does this work? I have a tuple. So I've isolated the memory that I'm going to share, and I'm going to put it into this tuple object. It's immutable, because those are final. I can only set them as part of the constructor. And then when I choose to write these values, I'm going to just allocate a new tuple. And then when I choose to read them, I'll read that. And the way that this works is because this P, right, is some kind of a pointer, like on a 64-bit JVM, that'd be a 64-bit pointer, that points back at this object. This right here is guaranteed to be atomic on a 64-bit machine. So you essentially have a 64-bit update of that pointer, so that sometime later, when you try to read it, you're always guaranteed to see something reasonable. Now, something I want to talk about is that you might read slightly stale data, right? So you have to be aware of that, and I'll show you how to fix it in a minute. It creates some garbage, so everybody here who's like a financial engineer is probably saying, I can't use it then, right? But I will say, this is a best case scenario for garbage creation. This is an immutable object that doesn't depend on anything. That's going to be easy to collect. The other thing is, it's if you're kind of in the typical case of having a lot of readers and a few writers, maybe you're doing this once a second or once a minute, right? That's a very low overhead to put on the GC, to add to your GC bandwidth. So it's something you can take on in typical settings. This works best in the single writer model. So in the single writer, right, you have one thread that writes. It's possible to introduce a data race if you have multiple threads that are writing and updating this, because you don't know which P1 and P2 that you're going to get, right? But that depends on the application. It's application specific. So anyway, so how are we going to fix this problem with the stale reads? So I want to introduce this concept of offense. So offense is a control instruction that provides an ordering guarantee. So load or store operations appearing prior to the fence, they're also called memory barriers, in case you hear that out there. They're guaranteed to be performed before those that occur after the fence, right? So we said we're just going to assume that nothing has any order. So the fence is the way that we're going to get an order. Anything that happens before the fence will be committed to memory, it'll be as it is, and transitively you see the after stuff after. So the way that we get access to fences in Java is through the volatile keyword. And I'm sure you guys have seen this before. So the volatile keyword provides the most primitive form of data race freedom that's available in Java. And probably some of you have used this. Like if you initialize some data structure like a Boolean initially, and then every other thread's just going to read it to determine if that data structure has been initialized, that might be when you would use the volatile keyword to solve that problem of data racing. Volatile keyword applies to both read and write operations. So half fence operations, which are actually a pretty nice optimization, are not available in Java. It's not supported by Java. Now, it's kind of interesting because C++ supports like sequentially consistent, relaxed, half fence, read fence, write fence. It has like the whole gambit. And Java is like, well, they have to work with what it has. So, when you pick your language, I guess you decide how much control you want over this kind of stuff. You guys know this, the volatile is, almost always inadequate to solve real-world concurrency problems by itself. And you guys know this because this increment operation, right, which is the classic example, it consists of 3 operations, right? It reads this out of memory, this variable, it increments it, and then it stores it back into memory. So there's no ordering here with some other thread that's come through for those operations. We haven't done anything to order it. We've just said that the reads and writes are going to appear in order from the standpoint of the processor. Okay, so here's how we fix our stale reads, right? And this is where a half fence would be nice, because really I want to fence the write so that no read would ever go in front of the write. But I want to read this out of the cache. That would be the most optimal performance scenario, but I can't do that in Java. All right, how's everybody doing? Margaritas are wearing off. So up till now, you should be writing data race-free code. I hope you picked that up from what I've been saying. Synchronized keyword has good performance. Don't shy away from it. You should be writing structured locks, right? That's really important in terms of being bug-free. So, all right, we can all go. The best practice portion of the talk is over. Now we're going to get really into the bad stuff. So hopefully you're prepared. This is the dark side. So the reason I say that is because a lot of what I'm going to talk about now is specialist stuff. This is the kind of stuff that most people don't actually need to do this. You would have particular domains where this is of value to you. So it may be interesting academically, but the average application isn't seeing this kind of demand. At Conversant, we're dealing with hundreds of billions of transactions literally a day. I like to think of it as a million operations a second. But it's volume that's second to none. So we have to think about this. We have to consider this because when we're executing code, we're executing code billions of times a second. And so we really try to squeeze as much as we can out of our algorithms and data structures. So one of the questions, that is always going to come up is how do you do that safely, right? And how do you build a business model around that so that you're not doing crazy optimizations, you're just doing the right ones. So, that's kind of what I want to talk about a little bit. All right, I told you to use locks and all this stuff, and I told them they're great and good performance, but what's wrong with them, okay? Mutual exclusion prevents parallelization. That's what I said. That's how I started it out. It's Amdahl's argument, right? Everything that doesn't run in parallel, which is most, or at least half of your code, determines the performance of your application. So once you're in that zone, you can't get out of it, and everything that you have to have running concurrently is just going to be a cost that you have to pay. Locks are hazardous. As soon as you get locks, you could have deadlocks, you have live locks, you can have starved processes. I talked about fairness. There's no progress guarantees, right? Some thread suspended, when's it going to come back? I don't know, you don't know, nobody knows, right? There's no guarantees. And it's hard to make it safe, and especially if you use unstructured locks, it's very hard to make it safe. Then let's also talk about data race freedom a little bit. So I brought up that model and I said, well, it's a good model and this is how we're going to think about it in terms of how the Java memory model works. There's basically two states, right? Your code is either data race free or it's undefined, okay? So you may not have realized that you signed up for that when you were using Java, but that is the case, right? Now, that's fine, right? We wrote unit tests and we did our best. But guess what? There's bugs, right? So probably your code is not data race free. Probably there's some bug in there that prevents it from being data race free. So that means essentially your code is undefined, which doesn't sound like a comfortable way to view your code base, right? It sounds awkward in a way, like maybe we aren't achieving what we were hoping to achieve. Then, to add one more layer to this, what about untrusted code, right? We're all using frameworks and packages and tools that we download off the internet and open source code, and it's all great, right? We love that stuff, and we support it. But did you review every line of that code? Can you trust every line of that code? Who wrote it? Was it some, college kid? Sorry to the college kids. In the middle of the night, after getting back from the club? You don't know if it's data race free. Right? So if you have untrusted code in your system, then this could be a challenge. And if you're running some kind of like a cloud provider or a cloud service where you, by definition, introduce untrusted code into your system, or like in our environment, we have a group that submits essentially JavaScripts to execute within our ad server. This is all untrusted code. The developers of the ad server don't necessarily manage that code. We have to be able to be tolerant to introducing it into our environment. And if we're expecting it to be data race free, how do we communicate that back and forth and prove that that is the case? And then just one kind of other thing, if you're going to be working with this kind of data structure, pretty much everything is going to be some kind of a fenced read or a write operation. So those are expensive. I'm going to show some numbers later, but it's like an order of magnitude slower to read some kind of a fenced memory location than to read it out of a cache. All right, so another concept that's kind of interesting, but I don't know if we can actually achieve it, is lock freedom. So when I refer to lock freedom, I'm talking about deadlock and live lock freedom. That doesn't mean you're not using locks, although a lot of times that's the upshot of it. What does lock freedom mean? It means that at least one thread can always make progress. That sounds pretty nice, right? We would like that. All threads will make progress in a finite amount of time. That's also very nice. If you could achieve this, right? There's no deadlocks, there's no live locks. It'd be a really nice guarantee to have. Okay, so you're waiting for the shoe to drop. It requires all operations essentially to be linearizable. And I'm not going to get into all of it. It's kind of an academic term, but the idea is that it's essentially that it's sequentially consistent, right? Your operations have to interleave in such a way that it guarantees that you'll always be able to make progress. And so there's a lot of academic debate around this and academic papers that are written with data structures that are impractical, but they spend a lot of time proving that it's data race free and it's linearizable. But from the standpoint of a real world application, it isn't necessarily what we're trying to achieve. It's, sometimes it's just a higher goal to be data race or lock freedom, to introduce lock freedom than we can achieve in a practical system. So it comes with a lot of baggage, and it's going to be difficult. And all of the data structures that I'm going to talk about from here on in, none of them are going to be lock-free in the sense that you can write a paper and prove that they're lock-free. Okay, so let's just throw that out the window. All right, finally, we're here, halfway through. Atomics. So atomics are introduced in Java 5 in 2004 and C++ in 2010. That was called C++ 11, interestingly enough. What are atomics? So atomics are how we're going to achieve sequential consistency in modern programming languages. Every operation on an atomic value is going to be sequentially consistent. So I'm going to talk a little bit later about compare and set, so I won't spend any time on it now. Set, that's your good old fenced memory write, so it's like the volatile keyword. Lazy set is interesting. It was introduced into JSR just to support nulling of objects in like data structures that might leak a reference, right? So you guys are familiar with this. If you're implementing a stack, right, and you return the object, but you leave the reference, it could sit out there for an unknown amount of time and essentially leak these references. So you should null those objects if you're implementing data structures, right? And so that's what lazy set is for. And what it basically means is no write operation will ever come in front of your lazy set. All the write operations will have total ordering. But any other thread that is going to read that value, it could still read a stale value. It could still read the non-null value because the lazy set is going to be setting the value eventually. It doesn't say when. All right, so finally, let's talk a little bit about CAS. So what is CAS? So if I have an atomic, what I can do is I can get its value, and essentially I'm copying it into some other reference. And then I have this instruction, which is actually at the machine level to support this behavior. It's going to lock the bus and lock that memory location. It's going to say, if the value in that memory location is the same as the one that you had before, or the one that you provide in this argument list, then update it, and only update it, and do that atomically. Now, what I want you to recognize here is, at a much more primitive level, this is just the RCU that I already showed you. It's just happening at the machine level. It's the same essential technique, though, where you're copying something, you're updating the value atomically, and only one thread can do that. So I'm going to introduce this concept of speculative racing, and no, I don't mean Wile E. Coyote, although he does that quite frequently. What are we going to do? So we're going to read and copy a serial number. We're going to optimistically read some protected value, whatever the serial number is protecting. And then we're going to use this really clever trick, which is that we're going to, after we've done all the work that we wanted to do, we're going to prove the assumption of concurrency after we've done it. So basically the whole thing is going to be contrived in a certain way so that we expect everything to fall through, and that we're going to say that everything was concurrent. And at the very end, we're going to test whether it was concurrent or not. And if that falls through, great, we won. Right? That's the most efficient way that you can read that thing, because you didn't block, you didn't wait, you didn't have any synchronization around it. But if you fail, then you're going to have to go through some other case, and I'll show you the code, but it generally involves spinning the processor. So this is the same code as before. You get some value. Now you can speculatively do anything you want right here as far as what the protected state is. And if I call this operation, remember I told you the machine is guaranteeing that the value in memory still has this value. So if this succeeds, that you're able to update this value, that means your speculation that it was unchanged was true. Does that make a little bit of sense? So this is the trick that we're going to use from here on out. Everything's going to be based on this. So if you don't get it, ask a question now. All right, good. You guys are right on top of things. Good audience. All right, so let's try to introduce a real lock. Let's try to build a lock from this kind of technique. So what are we going to do? So like I said, we're going to read a sequence number. So we have our good old P1, P2. We've introduced an atomic sequence number. We're going to read that value. We're going to speculate that we're concurrent. We're going to do whatever calculation that we want to do. And then we're going to verify that the sequence is unchanged. This is our read. Okay? Does that make sense? Now, the immediate thing that you can notice on inspection here is that this is concurrency with no writing. Right? I don't have to change anything. I'm just testing whether it was concurrent or not. So immediately you can start to see where the power of this comes from in terms of the performance here. But let's talk about writing. How do we write? Okay. So I think you'll immediately recognize that there's a data race right here. Right? I can't just increment the sequence number. That's a fail, right? As soon as I set this, these two values are no longer in sync. But the sequence number hasn't changed, so the read method is going to go ahead and speculate. So there's a data race here, so we have to fix that. So the typical thing that comes to everybody's mind is, well, if one sequence number doesn't work, let's try two. That's what comes to my mind. So what you're going to do, right, is read the first sequence number, speculate, check and make sure it matches the second sequence number, and then we'll have some sort of a code that looks like this, where you increment the first sequence number at the beginning of the write, and then at the end, we'll catch the second sequence number up to the same value. Does that make sense? What do you think? Can we have a show of hands? Do you think this works? Why? Okay, you guys are smart. Why doesn't it work?
The instruction reordering? Is that going to affect this?
Well, I can't. So this is going to be, these are all atomics, right? So there's not going to be any ordering here. Anybody else want to gather a guess? So let's try to logic it through. Okay, so what we're saying with the two sequence numbers, when they're the same, it's okay to read, right? If I change one, that means one thread is writing. So if they're not the same, then I can't. Then I can't read, right? They're both the same again after the first update. Can continue, I can read. So this process continues. What happens when two threads try to write? It just got crazy, right? So this code actually works, or the previous code. This code actually works for push-pull scenarios, right? Where there's one thread talking to another thread. But if you have more than that, if you have multiple writers, this doesn't work. So we need to do better than that. Let's see if we can do better than that. Okay, so let's keep with this. Okay, so we're going to say the first state, and I just have one sequence number here. The first state's okay to read. And then let's imagine that at the beginning of the write, I'm going to update the sequence number. So when it's 1, it's writing and it's not okay to read. Then I'm going to update it again at the end of the write block. Okay, so now when it's 2, it's okay to read again. And then I'll continue on, basically in this even-odd strategy, that when something's odd, that's going to indicate that it's being written to. When it's even, it's okay to read. And in fact, that's called sequence lock. So same as before. Here's the writer. The writer is more interesting. So what am I going to do? I'm going to start the speculative race here. I'm going to grab the sequence. Then here, I'm checking for evenness, right? You guys know your bitwise math. If it's even, and the value is unchanged. So here, by the way, notice this. This is shadowing. Sequence is shadowing the field. If the field is unchanged compared to what I thought it was, then I'm going to update it, and now it'll be odd. Right? And no other thread, after I've done that, can come through this test. Then I can do whatever I want. And here, this is the critical section. I can update things. And finally, I'm going to catch up the field value with the shadowed value plus 2. Now it's even again. Okay? So, you guys are following that? I see nods. And then, how do we read? So it's similar to what I showed you before. So I'm going to grab the sequence value, and I'm going to speculatively, or just sort of call it a lock token, a sequence lock token. Then I can get whatever value I want here, as sort of like I'm doing my optimistic read here. And then all I have to do, just like before, is prove that my optimistic case was correct. So the sequence lock matches the value, so this is unchanged, and it's even. Then I can return the result that I speculatively read. And this works great with when you have a few threads, because chances are, if there's only a few threads, that this speculation is always going to be true, right? But as you can imagine, there's another scenario. If you have a lot of threads, then the probability is that only one thread is going to succeed, but many threads are going to be failing, right? So you can see that this kind of speculative racing approach is going to be better for a few threads than for thousands upon thousands of threads. And we'll talk about that. I'll show you some numbers. Any questions about sequence lock?
When you talk about the threads, John, you're talking about the write threads, right? The ones that are actually updating that. It's the number of read threads wouldn't really matter.
No, because your read threads, they're going to spin as well as every time. Yeah, I mean, I understand what you're trying to say, but everything that fails this test is still going to spin here, and you're going to have another thread spinning your processor. So it still presents a challenge, right? But yes, you can read, multiple readers can read at the same time, and that's a good point.
And you're willing to discard the processing that you do in the computational effort.
Correct. That's
and
another
any
good
side
point.
effects that might have.
Right, very good point. I mean, hopefully it doesn't have any side effects, but yes, if it did, that would be a challenge here. All right, sequence lock is available in Java 8. It's called stamp lock. Sequence lock, the implementation actually I just showed you, is also available in Conversant Disruptor. It's called sequence lock. All right, so you guys got the sequence lock stuff, so let's move on to blocking queues and building queues. So what's a blocking queue? You guys all know it's commonly used in distributing load in servers, right? You put like sockets onto the queue and then you read them off in multiple threads. It's also typically the bottleneck in servers, right? Like I know people who say, well, I don't use queues, right? Because it's always the bottleneck. So if you're building your server, it might be a choice for you whether or not you just build a single-threaded reactor server that just immediately calls back and does the work in the same thread, versus putting it in some kind of queue and trying to distribute it out. But I think you guys know where this is going. Maybe we can build a better queue and not have that problem. All right, so we're going to choose a ring buffer as the basis of our queue. Hopefully you kind of know how to write a basic queue. There's other ways, namely using a linked list, but for the most part, nobody likes that because it's going to create garbage every time it goes through the queue. So enter the queue at the back of the line. We all know this, right? Like it's at the DMB. Increment the tail. Items leave at the front of the line, right? Increment the head. And the position in the ring buffer is just the location, the head modulo the size, or the tail modulo the size, right? This is all your CS203 stuff that I'm sure you guys all remember very well. Okay. Now we have a problem, right? So when we have two memory locations, we're going to have this head and this tail. And usually like one core wants to read the tail and one core wants to read the head. So it introduces this kind of funky problem that, it sounds a little bit academic, but it's actually a really serious problem that we face in developing high performance code this way. So this cache line, so we have two different cores, to get out of the way. The cache line is looking at the head value and the tail value right next to it. And the cache line in this other core is looking at the tail value and the head value right next to it. Right? So what happens when this core updates the head? Now it's not updating the tail, but it actually introduces a form of contention because it actually invalidates this cache line. Because this cache line is looking at that. Right? Same thing here. This cache line is looking at that. So this is called false cache line sharing. And there is, fortunately, a convenient solution to that, padding. Right? So we just pad our values out so they're separated by more than the size of a cache line, which is usually 64 bytes nowadays. Although in the past there was some different sizes of cache lines. So you can check your architecture, but anyway, pad it out enough so that they sit in different caches, and now you're happy. You can independently update this. So we implement this strategy in Conversant Disruptor. Basically, all of the atomics are padded out to take up two cache lines, so that nothing can sit next to it, in either cache line.
A quick question. Was the Java 8 supposed to have an annotation of some sort to account for this?
I don't know about that. And that's a good question. I doubt it, though. It doesn't sound like the Java way.
Right.
I would like to see that, yeah. Usually they try to rigorously avoid making any statements about how the order of the memory is going to be laid out in objects, and we have to kind of do a bunch of experiments to reverse engineer it, right? Saving their butts in the future when they want to change it, But yeah, if you know that, send it out. I'd like to hear about it. Okay, so let's try to see how we can build a concurrent queue, right? So I'm basically going to resort to the same strategy as before. I'm going to take 2 sequence numbers, 2 for the head and 2 for the tail. And so basically, like I did before, I'm going to update the tail sequence when I'm modifying it. And then when they're not the same, right, that's going to indicate that I can't update the tail. No other thread can update the tail. When I've finished modifying it, I'm going to increment the other side of the sequence, and then that'll indicate that we can continue. And here we have tail greater than head, so that means that the head can now read the value off of the queue. So I do the same trick. I'm going to increment when I want to modify it. That means no other thread can modify. And then I'm going to increment the second sequence number, and now the queue is empty. Okay, and this is called the disruptor. This is basically what was discussed in the Disruptor 1.0 paper. And I'll take a little detour just to talk about naming of things. Some people are like, Conversant Disruptor? I thought Conversant Disruptor is just a really good queue. Like, why are you calling it Disruptor? Okay, and I guess I'm taking my name from the original Disruptor paper where they talked about this. Now, some of you guys know that the LMAX Disruptor actually has a lot more to it than just a queue. It's a complete domain model. I don't have time to get into all that. But, it's basically supporting an event sourcing approach to dealing with your data, and it's frequently, a domain model that's used in like a lot of trading systems. So if you're working in that environment, you might be familiar with it. But Conversant Disruptor doesn't support any of that. It's not a clone or a copy of LMAX Disruptor. We're taking this concept of just building a really fast queue. All right, so I have 2. I'm not going to call it head 1 and head 2. I call it head and head cursor, tail and tail cursor. But what's the read going to do? Okay, I'm going to speculate, grab the sequence off the head. I'm going to check the value of tail, right? And this comparison is important to recognize because even if the tail has changed while this is happening, right? Because I'm not doing any test on tail, but tail can only increase. So this speculation will still be true even if somebody modifies the tail, and that's important. I'm going to do my check on the cursor. If the cursor still matches the value that I got, then I'm going to update it, meaning nobody else can now enter the critical section. After that, this is your old CS203 ring buffer code, right? I'm going to figure out the slot based on modulus. I'm going to return it from an atomic reference array. This atomically gets the value out of that array, right? I'm going to call lazy set to be nice and null it out so that I won't leak the reference. And then I'll set my head to match the tail when I'm done finally. Does that make sense? The right is pretty similar to that. It's exactly analogous. The only difference is that I'm setting a value here, and I'm checking the capacity here. I'm not checking whether or not the tail is greater than the head. But it's essentially the same process. I have these two cursors that are moving in lockstep. And so what you've seen actually is like the entirety of the disruptor code. I mean, this is really the concept. And everything around it is like support. So disruptor approach, and I'm referring to Conversant Disruptor because I don't think the LMAX Disruptor really has the same methodology. But the real thing here, and the reason why it's so fast, is this is parsimonious code. Like, there's nothing you can remove from this. I mean, it's as compact as you can make it. And that's why, we're seeing such good numbers in terms of the overhead and the throughput that we get with it. We find that speculative data racing is much quicker than locking. Right? It's an order of magnitude, or 2 orders of magnitude better than an array blocking queue, which does all the same thing using reentrant lock. I'll show you that in a second. The fairness is poor, right? Because we kind of talked about this a little bit, but if you fail any of these checks and you go out here and spin, I don't know when you're coming back from that spin, and nobody does, right? It's a hard problem to solve. But typically when you're using this kind of a tool, you don't care about fairness. It's not strictly lock-free. I talked about that in the academic sense. And you have to remember that the idle threads on both the read and the write side are probably spinning. So if you're not willing to spin your processor, then you've got a problem with this approach. I promised I'd talk a little bit about the timescales. So this is from the original Disruptor 1.0 paper. Talked about, so locking is around 500 nanoseconds. I dispute that a little bit. I think it's probably more like a couple microseconds for ordinary hardware. But in the case where you're locking among two threads within the same JVM, maybe that's 5 nanoseconds is coming from. But anyway, it scales out to, say, thousands of instructions. If you're doing something that involves thousands of instructions, right, like a couple of big methods, or 10 big methods, say, then locking is probably a fine approach. It's not going to dominate your performance. On the other hand, if you're doing something that's more like hundreds of instructions and you need to protect that critical component of your code, then you're going to need something like CAS. So CAS is more like an order of magnitude lower than locking in terms of the time that it takes. And then finally, if you're just have a couple of instructions or a handful of instructions that you need to protect, then you're going to need to not use anything, right? Then you have to use some kind of a single-threaded approach. Does that make sense? This is just basically telling you, when is the cost of this approach going to dominate your performance? All right, so I want to talk about the Dmitry Vyukov's MPMC. So it's basically the same thing as a disruptor, but he has this kind of clever take on it, which is that, maybe the problem with the disruptor, and I've been trying to point out, it doesn't work really great when you have a large number of threads. So maybe the problem is the contention that occurs between all these threads while they're trying to share these objects, the tail and the head, right? So what that idea behind the MPMC queue is that inside of every entry in the ring buffer, it's going to store the sequence. So now every thread that comes in can get a different view of the sequence, and maybe that will reduce contention. So it's a clever idea. So other than that, the implementation is almost exactly the same as the disruptor. Instead of this having an array of entries, it has an array of these cells that have the sequences in them. And then I'll go through. The read and the write are exactly the same. So it grabs the head value, it grabs the cell that's associated with that, and then it compares the sequence in that cell with the head value for the read. And if it matches what it expects to find, that means that it can modify this cell. If it changes, that means it either missed the chance, some other thread already did it, so it's stale, or maybe like the queue is empty or something like that. So yeah, and then so it breaks out and it falls through to this code where you can actually return the entry. The write looks exactly the same way, except for it does a set at the end. Everything else is identical. It's talking to the tail, not the head. But this is an interesting approach. So let's talk about performance. This guys, everybody's been waiting for it, right? So this is a simple benchmark, JMH. One thread talking to one thread, okay? Everything I'm dealing with here is multi-producer, multi-consumer. Not talking about push-pull at all today. I mentioned it once, but I don't even have time to go into it. This is all the multi-producer, multi-consumer, the more general case solution that most of us need. But I'm using it in kind of a push-pull way, right? Which is obviously giving the disruptor the greatest advantage in terms of performance because it doesn't have contention among multiple threads. Talk about that case in a minute. This is on the latest Haswell. We just got these boxes like a month or two ago. So these are latest Intel Xeons. And these are the numbers. Basically what we did was we measured 1 million objects, putting 1 million objects through the queue and reading them off again in a separate thread. How long does that take? So it's 50 milliseconds in Conversant Disruptor, about double that on the MPMC queue, and considerably more than that on the rest. You can see the numbers for yourself. But this I did want to point out, right? This is the array blocking queue. So this is the reentrant block approach to the same problem. And it's at least an order of magnitude better to do the speculative racing. Now everybody touts, all the internet enthusiasts, whiteboard optimizers, tout that the advantage of the NPMC is really when there's a lot of threads that you have contending. So this is an example of multiple threads talking to multiple threads. So the number down here is the number of producers and consumers. So it's 24 producers, 24 consumers, 48, 96. And I'm not going to say that there's a better one on here. I'm going to call this a tie. But what you should really take away from this plot, and by the way, it's doing the same exact thing. It's writing 1 million objects and reading 1 million objects using all these threads. But what you should take away from this is, in any of these approaches, both Conversant Disruptor, LMAX, NPMC, they all have kind of the same Achilles heel, that as you increase the number of threads, you're going to pay a huge cost for that.
As you increase the number of producer queues, or do the readers matter as well?
Yeah, I think the readers would matter, but not as much. And so it's what we were just talking about. In this case, for the disruptor, the reader does do writing, right? So it has to update the sequence. So it matters.
But only to the point where you've exceeded the number of cores that you have, right? So you want to stick with the number of cores. I mean, you're optimized to the number of cores that you have. That's why you pick 24 on your baseline.
I think even less than the number of cores, but that's
just for each seek.
So really, you want one talking to one. That's the ideal case. All right, so I can confidently say that Conversant Disruptor is the world's fastest Java blocking queue. I haven't seen any contradictory evidence to refute that claim. All of our benchmarking shows that it's significantly faster, at least a factor of 2, than everything else out there. It has been in production since 2012, so just because we open sourced it this year doesn't mean that it's brand new code. And the thing I want to say about it is it's a Java blocking queue. So all of you guys who have code that involves a Java blocking queue, we're on Maven Central. I encourage you, plug it in, try it out in your test suite, try it out in your performance benchmarks. See if your CPU cost goes down. See if your performance, your time performance improves. So it's something you can plug in. There's people on the internet that are using dependency injection to just inject Conversant Disruptor into their existing code. They don't even have to do a code change. Since it supports the BlockingQueue API, you can just put it right into your existing code. That other disruptor. I'm not going to spend too much time on it because I don't really want to get into this whole war of the disruptors thing. But the claim is that it's better for low latency applications. So if you're in that place where you really care about latency versus throughput, it might be something you want to evaluate. It's proven and widely supported. You can't argue with that. A lot of people are using it, so it's a good tool for a lot of people. It implements a domain model that's pretty common in trading applications. So for the financial engineering people in our midst, that maybe it's something that you want to look at, and maybe that domain model benefits you. For the rest of us, if we're just building servers, or we're using Netty or Vertex or anything like that, any of these frameworks that can use a blocking queue, then you're kind of in trouble with Disruptor, right? Because it's not the API that they're expecting. On the other hand, Conversant Disruptor is perfect because it just drops in. It's a blocking queue. You can use it in any of those frameworks I mentioned. So, if we can put this aside, the battle of the disruptors, I just want to spend 1 minute kind of talking about, what's next? What do we still have to solve in this space? And I think there's some interesting challenges, actually. So this whole talk, right, was sort of binary, right? Half of it was like data res free, and half of it was speculative racing. So which one is the better approach? And when is it appropriate to use which use case, right? I think if you looked at a system and it had speculative racing, strewn throughout it, it would be like a pretty, ugly looking system, right? It's like you'd have all these, races and spins, and, it seems like it would almost be bad design. But then at the same time, you want to take advantage of this performance component that it offers. So that's one of the challenges, right? When and where can we use this, and what's that going to look like in 10 years? We have the lock freedom question, and can we achieve a practical definition of lock freedom, or are the academics just going to take it and keep going off and trying to be linearizable? But one thing that we can say for certain, and the tone of this is very much already happening. I mean, it happened with C++ 11. This is going to continue to evolve in Java as well. But hardware memory models and programming language memory models are going to be more certain, they're going to be more well-defined, more spelled out. And I think this is very good for the programmer because it's basically all of the definition, all of the direction of this is heading in stronger requirements. So from a programming standpoint, the languages are just getting more and more user-friendly. The concurrency, it behaves more like you expect. All right, so a couple things. The sequence lock is Hans Baum at HP. That's his sequence lock. It's very good, very fast. I would recommend his collected works. Go out there, search them. He's got a lot of great papers. Leslie Lamport, LaTeX. I use LaTeX. This talk is written in LaTeX. Sequential consistency as well. Melissa, thank you. Thank you for the pizza. Thank you for helping us set up. And I just want to spend 1 minute on Conversant, or maybe 30 seconds. Conversant is an ad serving company. We deliver ads on the internet. From an engineering perspective, like I said earlier, the performance complexity of the landscape of the internet is really second to no other problem. It's like this organic thing with, millions of users, and like I said, we have, millions of operations, millions literally of opportunities coming at us a second. And so from a programming challenge standpoint, I don't think there's a lot of other environments that can match that. We're definitely hiring, and so get in touch with Melissa if you're interested in us.
Cards are over there next to t-shirts.
We support the community, we support open source. These are things that we value, and that's why we're doing this. All right, so this is kind of interesting. I love this quote, but I looked up online, where the quote came from, and it's attributed to several people. This one, I think, Snapshot is probably the most likely source, I guess, but we'll say anonymous wit. In theory and practice are the same, but in practice, they are not. Any questions? Yeah.
So the first transactional memory chips are coming out of Intel, if not they're already out.
Right.
What does that change in all of this, particularly from the Java programming perspective?
Yeah, I don't know. That's a good question. I haven't, this is, all this stuff, like every time there's a change to, these kinds of concurrency questions, everything kind of goes up. And, the way I think of it, I don't know, this is just pure speculation, but, so take it for what it is. But I think that data race free is probably eventually going to be the winner, right? Speculative racing is kind of the approach for now, right? And what we have to do is build systems that are able to do data race free as fast as speculative racing. That's really going to be the challenge. And so that'll give the programmers the most comfortable landscape to work in, and you kind of get a win-win. But obviously there's challenges inherent to that, but that's probably where it's going to head.
So there is a contended annotation. It's called contended.
Okay.
For false share.
Cool. I'll have to look into that. That's good to know. He said there's an annotation called contended that helps to pad for false sharing.
Isn't it in like the Sun library though? I think it's one of those things that might get blocked by 9 though. Somebody double check me on that.
It's been a few years I've been working with Java, so I don't know, but
yeah,
it's somewhere.
Yeah. Cool. Yeah.
So you did this in Java, is there an implementation of C++?
There's a million, ring buffers, lock-free ring buffers in C++ that you could look at. You could do the same implementation. No, I don't have a C++ implementation, but that's something there's a lot of people out there doing that. I think the interesting thing from the Java, perspective is this does put the rest kind of the concept that Java can't be as fast as C++. This is, we're talking about nanoseconds. You can debate about how many nanoseconds, but we're talking about nanoseconds here, and that's in Java or C++, that's what you're going to get. Yeah.
Where are any products or libraries that are using your disruptor?
Yeah, there are some, but it's very new, so I only know of 1 or 2. But I encourage everybody to try it. I think that you'll find that the performance is exceptional. I think whatever you put it up against, you're going to find that it lowers your overhead, lowers your processing time. So give it a try. Use it in your system and let me know. I'd love to hear feedback about who's using it and who's using it successfully. And if you have challenges with it, we're willing to make changes and take pull requests and all that. A lot of it's, one of the big things is it's heavily optimized for Intel. So I don't even think it would work on like power architecture or something like that. It's very Intel centric. So it doesn't affect anybody here, at least according to the poll earlier. But if anybody was in one of those environments, I'd love to hear from you and we could make changes to support that. Yeah.
I took a scan through the code before this talk and noted with approval that you don't use unsafe, unlike LMAX Disruptor. But I did see a couple volatile instances of volatile, but I didn't see those in your example. Can you tell me how they?
Yeah, so that's good. That's a really good observation. I don't use this atomic reference array actually in the implementation of Conversant Disruptor. So on Intel, we have causality, right? So I don't need that. If I know that the tail was updated, then I know that my buffer has been updated in memory. So I can make that optimization. So we exploit that. It's about a 10% improvement on Intel. In a weak memory model, you have to do this. So that's one of the reasons why I'm saying I don't even think it would work outside of Intel. Good question, though. Anybody else?